Hello, buenos dias, bom dia, good morning to everyone. Welcome to the Astronomy Department of IAG-USP. Thank you all for your participation here presentially or online through YouTube or this Google Meet call. Today we have a special conference here with Dr. Mónica Rubio, full professor of the Astronomy Department of the Universidad de Chile. Before we start her talk, I will give the words first to the Consul General of Chile, Dr. Juan Salazar Álvares. He will give a brief introduction to Dr. Mónica Rubio. Please, Dr. Juan.
Buenos días, buen día, good morning to everybody. Es un honor para el Consulado General de Chile poder estar esta mañana reunido con los profesores, con los investigadores del Instituto de Astronomía de acá de la Universidad de Sao Paulo. Especialmente también agradecer al profesor Milton, que representa a la FAPESP, que es una institución también amiga y cooperadora con Chile. Quiero, hacer una breve introducción porque el currículo de la doctora Rubio nos consumiría gran parte de la charla de ella y no es el objetivo de eso, pero creo, que hay que destacar que la presencia de la doctora Rubio está en un contexto de un desarrollo que Chile ha tenido en la astronomía. De acuerdo a las cifras que se manejan públicamente, nuestro país tiene aproximadamente el 40% de la observación astronómica del mundo, con telescopios de última generación. Por ejemplo, el telescopio gigante de Magallanes, el telescopio extremadamente grande del Cerro Paranal, que hacen que nuestro país sea una escuela para estudiar el universo. El norte de Chile también ha sido declarado como una tierra para la astronomía, ya que hay aunque hasta el momento se ocupa el 50% de la capacidad de observación, pero en los próximos años puede llegar a un 70%, por lo tanto es una actividad que está siempre en desarrollo. Actualmente Chile tiene unos 17 observatorios que suman unos 240.000 hectáreas. Y en este contexto entonces queremos destacar la carrera profesional de la doctora Mónica Rubio, astrónoma de la Universidad de Chile, que fue Premio Nacional de Ciencias Exactas el año 2021, doctora en Astrofísica y Técnicas Espaciales de la Universidad de París en Francia, y se desempeña como profesor titular y académica del Departamento de Astronomía de la Universidad de Chile. Es experta en radioastronomía milimétrica y ha sido astrónoma, profesora visitante en diversas instituciones extranjeras como la Universidad de Harvard, Yale, Berkeley, Columbia y Maryland en los Estados Unidos, y también en el Instituto Max Planck de Radioastronomía en Alemania, entre otros. Ella, ha promovido también las publicaciones científicas, el estímulo a otras astrónomas para que puedan seguir esta carrera apasionante que es el estudio del universo. Destacar que utilizando el radiotelescopio ALMA, la doctora Rubio descubrió nuevas estrellas que fueron publicadas en la revista muy prestigiosa Nature el año 2015. También la doctora Rubio es presidenta de la división medio interestelar y galaxias del grupo local de la Unión Astronómica Internacional y ha sido presidenta de la Sociedad Chilena de Astronomía en 2 ocasiones y vicepresidenta también del Consejo de Ciencia y Tecnología. Ha sido distinguida con premios como 100 mujeres líderes de mujeres empresariales y el Mercurio, y el premio Women Who Makes a Different Prize, entregado por la International Women Forum. Sin agregar más, no porque no haya más que agregar, sino para darle el tiempo realmente a la doctora que nos pueda ilustrar con sus conocimientos, irradiar esa motivación para la ciencia. Le doy, digamos, también a nombre del Consulado de Chile los agradecimientos por esta llegada acá a Sao Paulo.
Thank you, Dr. Juan Salazar. Thank you, Professor Mónica Rubio, for being here with us today. Now I'll pass the words to Professora Beatriz Barbui, a full professor of our department.
Eu queria completar que a Mônica, nós conhecemos a Mônica há muito tempo, né? Nós temos uma relação de muitos anos em congressos que ocorreram aqui ou em Chile, né? E então nós esperamos, essa visita torna o laço ainda mais forte e esperamos continuar com as nossas interações, né? Então pode apresentar.
Thank you, Beatriz, also our Vice Director of the Institute, Professor Mónica. Just a few announces. She's going to present the talk Studying the University from Chile. Questions can be asked to Mónica after her presentation, unless she says otherwise, of course. If you are following the talk using our channel, YouTube or Google Meet, you can also send your question, write down your question in the chat. And I would like to ask all the colleagues following this talk in Google Meet to please turn off microphones and cameras. And Mónica, please feel free to start.
If I may take out my mask. So, thank you very much. I'm really very pleased and grateful for this invitation from the Consulate of Chile to be here at Sao Paulo at the university and at the astronomy department. We have a long collaboration, and also I know many of the astronomers from Brazil, so I'm really very excited to be here. I will talk a little bit of why Chile has become so important for astronomy in the world, and also present you some of the recent results that I have on the scientific work that I have been doing lately. So, let me show you why Chile is such an important place for astronomy. First, we have in the northern skies, in the northern part of our country, very clear nights due to the fact, more than 300 clear nights, due to the fact that we have very high mountains, over 2,000 meters of altitude. We have very little humidity, which makes the atmosphere very transparent and stable. And we have in this area very little towns, although it is increasing, and we're trying to protect all these regions from the light pollution of the nearby cities. The fact that we have a very cold ocean in front of our coast and very high mountains produce this climate that is very good for astronomy, and that is why we have concentrated so many telescopes, and for a long time, more than 60 years now, since the first installation of the international observatories in our country. So here is a group, let me see, of different telescopes, in the ones that started on the 1917s with Cerro Tololo Inter-American Observatory, the first one. Then we have La Silla Observatory in the region near La Serena, and also Las Campanas Observatory. Later came another regeneration of telescope, much bigger in size. The size of the telescope is very important for the detecting very low luminosity and farther away objects. And we have the big telescope that the size of the mirrors went from 6.5 meters to 8 meters. And of course, we have this Brazilian telescope situated in Cerro Pachón. Yeah, the SOAR telescope, which has been working very nicely, and several collaborations with Chilean astronomers have been going on in this telescope, and also with the instrumentation like the Fabio Perot that has been developed here in Universidad de Sao Paulo. And of course the other big telescope like the 6.5 meter twin telescope in Las Campanas, 8-meter telescope Gemini, where Brazil is also a member of the Gemini telescope here in Chile, and its twin in Hawaii, and the VLT from ESO with its 4 telescope. So this is what we have right now, and this is the distribution of on the northern parts of the country in Antofagasta, and also in the 4th region of our country, about 500 and 1,000 kilometers from Santiago, the capital of the city. But we don't only have optical telescope. There has been a very big development in the area near the Chacnator Plateau, near San Pedro de Atacama, in the 2nd region near Antofagasta, of radio telescope that have been installed there, deployed there, since in this area it's very high, 5,000 meters of altitude. So the conditions for millimeter and sub-millimeter studies in this wavelength is very good as well, because the atmosphere is very transparent and we don't have too much, the water vapor is very low. And this means that several radio telescopes were deployed in the area, like this one, which is the APEX telescope, was one of the prototypes of the large ALMA array. We have Japanese telescopes, ASTE, Nanten, and cosmological telescopes that are also being deployed and being built, like the Simons Observatory right now, the Atacama Cosmological Telescope that has been working for several years, and of course ALMA, the big array with 66 antenna in the Chacnator Plateau, and in the future and starting construction, the Cherenkov Telescope array for high gamma ray observations of the universe. I have been working mainly on these 2 galaxies, which are nearby galaxies, the nearest to our system, which are the large and the small Magellanic Cloud, which can be seen in the sky in Chile, and I probably here when it's not cloudy, the Magellanic Clouds, the large and the small Magellanic Cloud. And the main reason that I have been studying these galaxies is that they can only be observed from the southern hemisphere, and also they have properties which are different to the ones that we find in our galaxy, in the gas and the medium which is in between the stars, with much less component of the carbon and oxygen abundances than in our galaxy. So in order to make the study of the regions where the star formation process is going on, we need to use other tools than the optical, because now we know that these regions, the regions where stars are formed, are dark and dense and very cold, and they do not emit in the optical, but in radio waves. And also in the infrared waves. So one way to observe this region is using the thermal emission from the objects. And here is an example of during the night, we don't see. Yeah, if there is someone here, because our eyes and the telescopes are not sensible to this emission, but if we use the thermal or a special infrared lenses, like the night vision lenses, then we can see that there is someone there because it emits temperature, 36 degrees, the temperature. And of course, since the last 3 years of pandemia, we're used to be measure our temperature with these devices everywhere. It's the same that we use in astronomy, because in this kind of emission is the same one as the optical emission, the visible, over a large range of different wavelengths or frequencies. It's a family of the same kind, which is called the electromagnetic spectrum. And because the eyes were the first detector that we have, natural detector, well, most of the astronomy was developed during many years in the optical. But today, the universe emits in all these wavelengths, and we are able to observe in all of them. And in order to do that, okay, we not only have the telescopes, but we have the radio telescopes that can be based on the ground, but we can also explore all the universe in the other regimes, just putting over the atmosphere space telescopes, or with different detectors that can detect the emission from the gamma rays to the infrared, because the infrared also does not get into the ground due to the absorption in the atmosphere. So, as I was telling, in order to study the regions where new stars are born, we know now that the stars are born inside very dense clouds of gas, which are cold and dark. And in order to explore those areas, we need to use these other techniques, like the infrared wavelengths, the infrared telescopes, or the radio telescope. And the telescope I have been using in order to explore the Magellanic Clouds are being mainly a radio telescope, APEX, and Herschel, a space telescope that was flying over in the atmosphere for several years. And I will show you some of the results we have on these regions. So I'm an observational astronomer. I've been using all the telescopes, this large variety of telescopes that I show you at the beginning, which are in different summits. And I love to go and do observations myself during all these years. I've been in all the various summits, and here are some examples. And not only at the radio telescope at ALMA, but also here you can see with my students doing observation at the 5,000 meter of altitude in the APEX control room, and as well in the other telescope. So I will show you some of the recent results that we have. And I was exploring in the small Magellanic Cloud, which can be seen here, the regions where these dark areas, these dark clouds where new stars are born, exist. And for that, we used different radio telescopes, and we were able to make a full map. And on the white spot, you can see contours where we found the existence of these CO clouds. And also with another radio telescope, we were only able to explore very specific areas, but we didn't have a full coverage of all the emission at a resolution that allowed us to determine the physical properties of the molecular clouds. So in this region, the first thing that we found was that in our galaxy, since these clouds are emitting also in our galaxy in the millimeter, and the main emission is due to the existence of a molecule, which is the CO molecule, we had to convert the emission of the CO molecule into a mass of the clouds, one of the main properties that we need in order to study star formation. And in our galaxy, it had been derived that the proportion of the emission of the CO molecule and that of the molecular hydrogen, which is the main constituent of these dark, dense clouds, was a factor of something that 1/10⁵. And we have this factor being calibrated, and we found that for the SMC, this factor was about 10 times higher than the factor that we had in our galaxy. And as we increase the diameter of the radio telescope, the resolution of the telescope gets smaller, and we can see with greater detail. And this meant that when we were observing with a beam size of 140 parsecs, we found this calibration, this difference. But when we were observing with a beam size of only 20 parsecs, well, this conversion factor turned out to be only 4 times the fraction, the conversion in our galaxy. So that meant that resolution is important for extragalactic work, and we have to consider the fact that if we are observing what we call giant molecular clouds, 100 parsec, well, in this kind of galaxies with low metallicity, low carbon and low oxygen abundance, then this conversion factor is different in order to determine the mass, which is one of the physical parameters that we want to know. And we recently finished a big survey of the SMC using the APEX telescope, and we were able to map all these regions in the small Magellanic Clouds. It's a big galaxy, so it's not easy to observe it completely. This took us about several years to finish this work, and these were the regions that we found. This work has recently been accepted for publication, and these are some of the results that we have found. Now we have a resolution of only 9 parsec, 10 parsecs. Half of the previous resolution, and we now are able to determine some physical properties of these molecular clouds. And what we have found is that, for example, if we correlate the size of the clouds with the velocity line width that we can measure from the CO emission, well, the SMC molecular clouds behave very similarly in the slope than what has been found in the galaxy, which you can see in this dotted line. But for the same radius, the galactic clouds are much more luminous in CO than in the SMC. Since we have a good resolution to determine the sizes of the clouds, we can now also estimate what we call the virial mass, assuming that the clouds are in gravitational equilibrium. And in this case, what we have found for these clouds is that if we measure now this conversion factor, which is how to transform CO to molecular hydrogen, but now we have another way to determine the mass, which is from the virial. We found that for the molecular clouds in our galaxy, this is the mean of that we found in the galaxy. But for the SMC, we found that this factor is about 3 times the one that we have found in the galaxy. So we are now going to low resolution, but we still find a difference between what we find in the galaxy and what we find in the SMC. Also, in this study, we were able to determine, for the first time, we have almost 200 molecular clouds identified, so we can do further studies, and we determine the cloud mass distribution of these molecular clouds in the small Magellanic Clouds, and we found that most of the clouds are dominated by low mass clouds, 10 to the 3 solar masses, which is different to the one that we find in our galaxy, which is much higher. In our galaxy, we have 10 to the 5 solar masses molecular clouds. We also studied the stability of these clouds and to see if the assumption of gravitationally bounded clouds was correct. And here we have a plot in which we have what is called the virial parameter and the surface density of the molecular clouds. And these are the lines for virial equilibrium, and these curves here represent external pressure, because the clouds can be bounded because of gravitational equilibrium, or they may need, if they are in a turbulent medium, they can have a pressure in order to confine them. And as you see, we find that most of the clouds are mainly in virial equilibrium, and here you can see also the clouds in virial equilibrium. And in this study, we were also able to include a third method to determine the masses of these molecular clouds, since there was a study which the masses of molecular clouds had been determined by a third method using the dust emission from the clouds, and we had the masses derived from this dust emission, and we compare them because they were done at similar resolution, those masses, and we see that the clouds which had also dust emission and CO emission, these are the ones in green here, they also behave in virial equilibrium. So the main result also was that although the clouds seem to have similar properties, the factor to convert from CO or to virial mass to determine the amount of mass in this galaxy turns out to be different if we use the virial mass, which is only 2.5 times the conversion factor that we have in our galaxy, while if we derive it from the dust emission, this is much higher. This, of course, this results is dependent on the properties and the condition of the dust emission, which were assumed in this other study by Takekoshi et al., typical values for the Magellanic Clouds. Now, with ALMA, we can have a much better resolution to study these molecular clouds and go into 1 parsec resolution. And I will show you some results we have. For example, we have observed this region, which is called the Magellanic Bridge, which is a bridge that was discovered on neutral hydrogen long time ago. And now you can see that now with Gaia, we see that there are also stars in this region, and we have some areas in which CO emission had been detected, and also dust emission was detected with the Herschel satellite emitting at 160 microns. And we studied then these 3 clouds which are located on the Magellanic Bridge, which has also some different conditions from the SMC interstellar medium. And we found out with ALMA in one of the clouds, and this is a study that was made by one of my students, Teresa Valdivia Mena. We find only 2 CO clouds, and we determine the properties of these clouds. And we also find that these clouds are very tiny, very small, and the emission from CO is very concentrated, and the density of these clouds is much higher than in the Milky Way. Similarly, this is another study that we did with a postdoc. We found for the Magellanic Bridge C, we found that in this region we found 12 molecular clouds, again with very small sizes and very narrow width, line width, which density, surface density, much higher than the galactic counterparts. And for these clouds, we were also able to determine the conversion, and we found that this conversion is about 2.5 the times of our galaxy. And this means that even if we now are resolving these molecular clouds at 1 parsec resolution, we don't reach the conversion factor in our galaxy. And that has to do most probably with the structure, the photodissociation structure of the molecular clouds. And this is recent results. We have been doing a survey which was finished by ALMA of all this region in the Magellanic Cloud. And here you can see a first image where we see many, many clouds, and more now a more filamentary structure of the clouds. And we are on the process of analyzing and deriving all these properties, so I cannot show you any result yet, but just a nice image. And also a second image in here we can see not only the CO clouds in red, but also in blue the X-ray, and in green the H1. So a nice set of data to obtain the results now at less than 1 parsec resolution with ALMA. The other cloud that I mentioned, the Large Magellanic Cloud, is much bigger. So all the studies have been concentrated in different regions, and I will just show you one region that we have studied. This is the distribution of the molecular clouds in the galaxy in the LMC. That was done in 2008 with one of the radiotelescopes, with the Nanton telescope. And this is the distribution of H1 done in Australia. And I will concentrate on the 30 Dorados region, which is the biggest and more luminous supergiant H2 region that this galaxy has, with a cluster called R136 that has a very luminous and very massive stars which are more than 100 solar masses, and that emit a lot of ultraviolet radiation that would destroy all the molecular clouds in the regions nearby. So we didn't expect to find any molecular clouds very near of this region, because either they were destroyed, photodissociated, or with the very strong winds that the stars have, they would have been dispersed, and that is why we can see in this region the central cluster in the optical. And surprisingly, nature is more complicated, and we were able, with ALMA observation, at only 10 parsecs of the central cluster, we were able to determine about 12 molecular clouds which had a velocity graded in the area. Here's R136, the cluster. This is the beam size, and here are the different clouds. And again, we were able to determine that another work, a second work of my student, and even smaller sizes and very much denser clouds that were able to survive in this very violent and extreme regime. Again, we studied the properties of this set of clouds that we observed and we found, and the main reason is that the CO molecules that are near R136, some of them are gravitationally bounded, but others do need an extra, cannot be sustained only with self-gravity, and we found that the conversion factor in this very energetic regime is even larger than we have found in the SMC or in the Magellanic Cloud, meaning that probably photodissociation has been so strong that only the very densest part of the molecular clouds in CO is still has survived. And the last work that in which I have been involved with a big consortium now is with observation with ALMA of all the region in 30 Dorados, and this is the map that we recently obtained, and we can see this is where the central cluster is, and you can see there's a lot of molecular clouds in this region, and this is the comparison between the CO in red and the nebula in the optical, and or the infrared, the gas, and you can see that there are kind of fingers, yeah, pointing to the R136 cluster, and the first result that we have obtained from this study is that, again, the science lines with relationship holds for this set of clouds, but they are different to the ones in the galaxy. There's always a shift. The correlation, the slope is the same, but there's a shift. On the line width, we have, for the same radius now, these clouds are much higher line widths, and also most of them are in virial equilibrium, although the mean deviates from virial equilibrium, implying that we need some other another component in order to explain the stability of these clouds. This is a summary of the results that we have in the small Magellanic Cloud and the Magellanic Clouds, but the main takeaway for this of all this study is that the way to obtain a mass from CO emission is very dependent on the properties of the interstellar medium, the abundance of carbon and oxygen, and it's not a universal factor that you can just use and apply it in any galaxy. You have to consider a type of galaxy and the conditions in the interstellar medium. Another work in which I was involved was this galaxy, WLM, which only had 13% of carbon and oxygen. The small Magellanic Cloud has 20%, the large Magellanic Cloud has 50%. So the idea was to study star formation process in galaxies that have this gradient of metallicity in order to try to understand how the process of star formation was at the very beginning of the universe, where almost no carbon or oxygen existed, and see if the process and the properties of these clouds were similar. The first things that we did was to observe these clouds with the APEX telescope, and we pointed into the 160 micron emission that had been mapped by Spitzer telescope, and we were able to find for the first time in such a low metallicity galaxy the emission from CO. And of course, immediately after, we went with the team to observe, and we proposed to do this with ALMA, and these observations turned out to be to identify very, very small CO clouds here, about less than 1 parsec in size, and very dense and not very massive, only 10 to the 3 solar mass, 10 to the 2 to 20 to the 3 solar masses of this cloud, which implies that in this kind of galaxies, formation of big cluster of stars is probably not very common, but one can explain then that even in galaxies with so little contact of molecular of carbon CO, still once the CO is formed, the star formation process can go ahead. This is a nice view of the ALMA telescope, which allow us to make all the said at the beginning. This is how we see the northern region of our country, always clear, yeah, from the 4th region to the 2nd region. This is the place where ALMA, the big and all the radio telescopes are located in this area. Okay, this is an image from the Hubble Space Telescope taken from the northern part of the country. And this means that the future is fantastic. As the consul was telling, Chile now holds about between 60 and 70% of all the astronomical facilities in the world. Due to this condition, they have concentrated in the northern part of our country, and in the future, this will be even higher with even bigger telescopes. We have here the 4 projects that are now being being designed, or several of them now are being in construction. As you can see, 3 of the 4 will come to Chile, and unfortunately, this 30-meter telescope has not yet started construction, or it is well defined if it will be finally built. It would go to the northern hemisphere, so unless TMT can fly, the largest gigantic telescopes will be in the northern part of Chile, having 100% of the most advanced telescope in the region. And these are huge machines, okay? This is the extremely large telescope that is being built by ESO and Australia, and this is the size of the Arc of Triumph in Paris, so it's a huge, huge, and we have here the giant Magellan telescope, in which Brazil is also collaborating and is a member. The University of Sao Paulo is participating in this project, and we have also the Vera Rubin or Large Synoptic Telescope. So these are huge instruments. This is a 25, the GMT, 25-meter equivalent mirror. The extremely large telescope is a 39-meter telescope, and the large synoptic telescope, or the Vera-Rubin telescope, although its mirror is only 8 meters of diameter, it will produce terabytes of data every night, challenging a new way in which astronomy is going to be done in the future, where development, all the data tools of big data are being necessary in order to be able to analyze and to extract all the information of 30 terabytes of data that will be produced every night. The total, here's a list of the international observatories that we have now in operation or in construction. There are several others which I will not go now into detail, but this means an investment of more than $6,500 million in the country. The agreement that Chile have signed with all these international observatories, both at the level of the government and the University of Chile, have included that 10% of the telescope time can be used by the astronomers working on Chilean institution, of course on a competitive basis, but this is a big possibility to explore collaboration. And although in Chile we have increased the number of astronomers in the last 20 years, very, very much. Here we have how the number of astronomers have been rising since 1994 and 21. Now we have also 27 universities which have astronomy groups all over the country, more than 250 astronomers and faculty with PhD, and a lot of students, very much interest from the young students to study astronomy, over 500 students, and also we have now graduate studies, both master and PhD in several of the universities, and we have about 200 or more students in all the programs. Statistic of what is happening in astronomy, and these numbers increase every year. So in the Chilean Astronomical Society, SOCHIA's webpage, we try to have this statistic online, and every year we update it. Just to finish, well, Chile by now has this large concentration of telescopes and radiotelescope and infrared also telescope. In our country, we have the possibility to use this old telescope due to this agreement that the Chilean government and University of Chile has signed. And of course, there's a lot of possibility to collaborate. So please think about extending the collaborations that we have had with Brazilian astronomers. I must say we have an astronomer that was formed here at the University of Sao Paulo, Amelia Ramirez, that started the astronomy in the Universidad de La Serena, a group which is now much bigger, about 12 to 15 faculty, has grown a lot. So both Amelia Ramirez and Hector Cuevas are alumni from University of Sao Paulo. We also have collaboration and interaction and interchange with different universities with Sao Paulo, and there are some Brazilian astronomers that are working in Chile, like Marcio Catalán at Católica University. And of course, we are open to extending these collaborations. And I would like to invite you all to the next annual meeting of the Chilean Astronomical Society, which will be held finally in person on March of this year, the second week of March in Temuco, in Chile. And the webpage is already online, so please consider registering. And these are the occasions in which all the astronomers can gather and start new collaborations, and we will sure that we will be most happy to increase this collaboration and also to strengthen the collaboration between our countries. So thank you very much.
Thank you, Professor Mónica, for the very nice talk, very clear. And now we would like to open if someone would like to make some questions, comments. So we have one there. I'll bring the microphone.
Thanks, Mónica, for your great talk. 2 questions, if I may. First, in the astrophysics part, when you're talking about the, I believe it was the LMC, right? That you needed some extra physical mechanism to support some of the clouds, not just gravity. Could magnetic field play a role there? That's my first question.
Yes, of course. One of the possibilities are magnetic fields. I have also been a little bit scared of magnetic field. You are the expert, no, on magnetic field. I haven't seen any results regarding the Planck results on the magnetic field that could be used to include in the support of molecular clouds. The scales are not comparable. We need to go to much smaller scales in the magnetic field. So I don't know, but surely this is one of the, and the fact that now we're seeing all this with the ALMA data in the SMC, and also with the, we're seeing this kind of filaments, okay, and these are very similar to the ones that we are seeing in the galaxies, and there we see that the magnetic fields are really important on the simulation in order to produce these filaments, and then you have the star formation where the filaments cross. I think this is this could be something that we're starting to be able to resolve in this region. Yeah,
just to complement then, since you put the ball in the penalty mark, I would just mention that we had a small survey on the SMC, on the northeast and the wing part, and we have some measurements, some estimates, well, let's say, using equipartition for the random field and actually dispersion of polarization angles in that part, and so we had estimates of the field. That's a more or less recent paper that we did with a student from here. So there are values. I mean, maybe that you may want to consider eventually. Yeah.
And that is in the northern part of the SMC?
Yeah, the northeast and towards the bridge, yes.
Okay,
right.
That's very interesting, because there's a group of Japanese that have mapped the northern part with ALMA.
Okay.
And just published last year, but only the maps, and they haven't published yet the properties of the clouds. They probably are on the way over there, but that covers that northern.
So which
Tokuda et al. 2021.
Right, and that's H1 or CO? Is that, do you remember?
These are ALMA observations. Yeah.
Oh,
CO.
Okay, CO, right?
Yeah,
okay,
CO.
great. Yeah. Okay, great. Yeah, we can discuss that later if you want. We also, yes, great point. the other part, I mean, in the general picture, I mean, you mentioned, I mean, my first time in Chile was 1978. I guess nobody was born here back then. But anyway, okay, yeah. So yeah, so it was very impressive. Every time I go to Chile nowadays, I mean, it's incredible. I mean, the scale of development is impressive. So, in addition to the nice development, the graduate and the graduate studies, does Chile? I believe Chile. I know that there are some radio, or submillimeter groups in Chile. Is Chile also considering, investing in the establishment of telescopes or equipment and so on? Can you give us a little snapshot of that, please? Thank you.
Yeah, this is astronomy 2.0. That's how we call it, in the sense that now the community has enlarged. Many universities are doing astronomy, and there are several groups in this university that have instrumentation groups. That the main idea is to participate in the development of instruments that will go in this telescope. And for example, we have at the University of Chile the millimeter wave laboratory that produces the optical part of the receivers of band 1 for ALMA, and is now involved also with some developments on the optical part for some of the receiver for JAMA, in which Brazil is with Argentina are working. There's also groups in Concepcion that are doing another laboratory. So there's quite several groups also in the optical with infrared optical spectrometers that are being deployed in the 1.5 and the 1 meter in La Silla, also built by the Astro Engineering group at Católica University. And as you know, instrumentation requires funding and requires long-term funding, because you have to set up the laboratories, you have to build the prototypes, you have to test. And this is a long time adventure that requires sustainable on-time funding, and we're trying to convince the different authorities and government to support this initiative. There's one fund that was started in 2013 at our funding agency, which is now moved from CONICYT to ANID, which has about $1 million at that time. Now it's less in pesos, maybe it's about 700,000 US dollar equivalent, and specifically for developing instrumentation. But our hope would be that Chile could participate in a much more aggressive way, because we have the know-how, we have the people, and we can join this partnership with other countries and develop instrument, which is the way to go in the future. So yes, and we hope, and I was now that the Consul General is here, that we get the support that we need from our authorities to strengthen the instrumentation program in Chile.
Thank you for your nice talk, Monica. One question is, when you talk about the conversion factor, let's say, you are willing to use the CO observations to deduce what is the total mass of a cloud. Do you imply that, let's say, all the hydrogen is in the form of molecule, H2 molecule, or there is a mixture with, let's say, normal atomic hydrogen? And related to this, I put another question. I was happy to see that in your talk you never pronounced the word, let's say, dark matter. But in the past, many people would have said, well, what is keeping the things together is dark matter. What is your impression about that?
Okay, well, the models, the PDR models that explain how CO is formed from H1 to get to the air, show that there are big envelopes of molecular hydrogen that are not being traced by CO. And in these envelopes, you can find other constituents like carbon, neutral carbon, or excited carbon, C2. Okay, there are now some results from carbon from C2 with SOFIA telescope, and also some carbon-1 measurement that do show that most of the envelope is still molecular, okay? And the observations confirm and are consistent with the PDR models on the amount of excited carbon and neutral carbon that has been observed. This is a challenge because to observe ionized carbon, you need to go to the far infrared, and the only way to do it until now was to using the stratospheric telescope of the NASA, SOFIA. Unfortunately, it's not being to continue its operation, so we don't have the possibility with James Webb. So until there's another infrared mission in that part of the infrared spectrum, we are blind. Okay, but the few work that was done with the SOFIA shows that still it's molecular. And with respect to H1, well, we need the much higher resolution for the H1 observation, because now we're at 1 parsec. Okay, and you always assume that the models and what we know from our galaxy, once you pass a certain AV, all the H1 goes into molecular hydrogen. Okay, it's a transition, and there's not too much atomic hydrogen at the size of the small molecular cloud. So in that sense, unless we have observation of H1 at that resolution that we can compare, and also the H1, the line widths are much, much extended than what we see on CO, several 10, 20 kilometers per second, okay, the line width of the H1 in the SMC. So I don't know if you mean with respect to dark matter or the dark CO. Is it that dark matter? Well, many people call these areas, these envelopes, that we cannot see because we only see what we can detect. And if they don't emit CO, we don't detect them. And molecular hydrogen, we cannot detect it as well. It's invisible for all purposes. So since dark has become very popular, there are many people that call these envelopes dark CO, but they are constituted of molecular gas that is not emitting CO. With respect to dark matter, well, dark matter is more to understand how the galaxies can show these rotation curves that continue, and there's some other kind of matter that needs to be present in order to explain the rotation curves in galaxies. With respect to dark matter in the Magellanic Clouds, there are some studies about stability of the clouds using dark matter simulations, but it's very difficult to obtain the observational evidence. And there is a group in Católica that is working on that, but I haven't seen any results recently about the observation they were planning to do, because they can study the binaries and assume dark matter presence in order to study the binaries. So that is what I can tell you.
Monica, I have a comment and a science question, if I may. The comment is with regard to instrumentation that you mentioned that in Chile they are developing these instrumentation efforts, and this is very important with government support as well. So just a comment on the gamma ray energy section. There is also some starting collaboration at the framework of a CTA, the Cherenkov Telescope Array, and also the precursor of the CTA, that is the Astronomía array that is in construction in Tenerife. And there are some engineers from the University of Concepcion who are involved in our collaboration because they can share with the Astronomía array and the CTA their experience on the interferometry. You know, interferometry in ALMA will be applied as well with the array of the Cherenkov telescopes. So there is already this collaboration with the engineers from technicians from the University of Concepcion with us in this. So this is very interesting. The science question that I have for you is with regard to the clumps, because you have measured the distribution of clumps in the Magellanic Clouds, and you know, these clumps, some of them are star-forming clumps and others are not. And there is a ratio, and this ratio is important for studies, theoretical studies of star formation, as you know, and also the influence of magnetic fields in these late stages of star formation. So my question is, do you know if the ratio of star-forming clumps and non-star-forming clumps is more or less the same as in our galaxy, or there is or it's still too early to say something about this with your...
The ratio between? I didn't catch it.
The proportion.
Yes.
The ratio, the proportion between star-forming clumps and non-star-forming clumps in the Magellanic Clouds, if it's the same as in our galaxy or not.
Okay. That's not an easy answer, because in order to start to know which of these clouds have star formation and which have not, you have to know, well, you can do an association between H2 regions, for example, or the presence of young stellar objects. We did that for our work in the SMC, and we found that about 50% of our clouds are correlated with either H2 regions or young stellar objects. But these are all, for the young stellar objects, these are very limited results, because the deepness of the observation of the YSOs done with Spitzer or with Herschel is not that. A smaller telescope, 3.5 meter telescope, is not enough in order to say if we're observing all the young stellar objects associated to the molecular clouds or not. So we haven't done yet much further to estimate in order to say which is the ratio. Also in the galaxy, due to the distance ambiguity, it's not that easy also to estimate that proportion. But now we are aiming with the JWST to have the infrared observation at higher resolution about the distribution of young stellar objects in the Magellanic Clouds. So we hope that the proposal is approved at some point.
Okay, I myself I have question. I remember you said that interpreting.
Can you take because it's difficult to.
I remember during your talk in the first part, you said when interpreting or modeling some data, I think interpret some data from SMC, you had to assume some model for the dusty properties there. How well do we know the dusty properties in SMC?
Well, that's the question I always ask to the people who work on dust. Yeah, because the the dust emission is not. Let me see. What we know more or less from the results that we got from Herschel and from Spitzer, quite a good estimate of the gas to dust ratio, because that is one of the things that you need. But the millimeter continuum emission that we have done, when we show that the millimeter dust emission is much, much stronger than the models or the grain properties or the dust properties that we use to use for the estimating the dust emission. And if you use a beta of 1.8 or 2, well, the dust emission from the clouds that we have observed in the SMC and also in the Magellanic Ridge is much higher. And none of the models, even the ones that DRAIN has produced using dust with magnetic component and another composition of the dust grain, that he modeled in order to explain the global dust distribution that we saw, the continuum distribution that we saw with Herschel, on the infrared, does not reproduce on the millimeter and the sub-millimeter the emissions. So there is a, not only on the Magellanic Cloud, but in low metallicity galaxies, a sub-millimeter emission, which has not been, we don't know what is the reason, the cause of that sub-millimeter emission. And well, I have been trying to do this continuum emission, dust continuum emission in some of this cloud, but I have not been able to convince the TAC from ALMA to give me the time, so I will try again in order to be able to have at least band 3 or band 6 emission on the sub-millimeter to measure, because we have a limit in one of the clouds, and we need to go much deeper, but the emission is much stronger. So it's very dependent on the properties of the dust, and we use the standard properties and what has been developed in the literature, and mainly the different models.
We still have a lot to learn about.
Yeah.
Okay, thank you, Professor. Some more questions? If not, let's thank again Professor Mónica.
Thank you very much.
Thank you, Professor. Now I'll give the words to the General Counsel of Chile, Dr. Juan Salazar.
Our sincerely congratulations to Dr. Mónica Rubio for her astonishing presentation. I know that the majority of you are related to the field of astronomy, some of us not, but still we followed with a lot of interest, attention, and comprehension of the issues that Dr. Rubio was explaining. Thank you for sharing also your questions and comments. To say thank you to the Institute of Astronomy, the General Consulate of Chile would like to announce that we brought a donation of 15 books. It's a book very interesting because it makes a summary of all the installation of astronomy in Chile. The book is called Chile, an Open Laboratory. And I would like to, in this moment, as a sign of appreciation, of thanks for the Institute, to deliver one copy for Professor Beatriz.
Muchas gracias, muy interesante. Estamos todos muy interesados en todo lo que pasa en Chile en telescopios e instrumentos. Muchas gracias. Y gracias por la visita y por todo.
Thank you, Beatriz. Thank you, Dr. Juan Salazar. So I'd like to thank you, Professor Mónica, again, for her time, for sharing her knowledge, her discoveries. And I would like also to thank everyone present here or following this conference via Google Meet or YouTube. So let's close now this meeting. Again, thanking again Professor Mónica and the authorities here present. That's it. Richard, we can